So here we have the piston, cylinder, crank inside of an engine. Then this is the crank, which has length of LC, which is 0.1 meters. And omega, we'll say, is 500 RPM. It's going pretty fast. Then the length of the rod is 0.2 meters. And we want to find angular velocity of the rod, linear velocity of the piston, angular acceleration of the rod, and linear acceleration of the piston at t equals 0.25 seconds. And this omega, given as 500 RPM, this is constant. So steps to solving this one. First thing we need to find is position of the crank and the rod. So we say this is positive x, this is y. With our coordinate frame, then this angle is theta c, angle of the crank, and then this is angle of the rod, angle given with the positive x-axis. Then the second step, we can find angular velocity of the rod. Then to find the linear velocity of the piston, then we need to find the position of each of these points. So we'll say this is point A, this is point B, and then the piston, we can make that point P. So we need to find the R's, those position vectors. Once we find those, then we can get piston speed. So that'll kind of give us the first half. And then to get the accelerations, then we just keep going with that. So next we could find angular acceleration by differentiating the velocity. And then we can get linear acceleration by differentiating the linear velocity. So actually step 0 could be convert the angular velocity, which is in RPMs, to radians per second, because we need to do everything here in radians. So 0, convert omega c to radians per second. So to do that, omega c equals 500 revolutions per minute times 2 pi radians per revolution times 1 minute 60 seconds. So we can see, all right, units canceling. This will give us radians per second. And this is 52.36 radians per second. So now we can get these angles. Well, we know that since omega equals d theta dt, then integral of d theta equals integral of omega dt. Now we're going to assume that theta will start at 0. So that means that the crank is straight along the x-axis. So here we'll have from 0 to theta c, from 0 to t. And this gets theta c equals omega c times t. equals 52.36 times 0.25. This equals 13.1 radians. So that's theta C. But we also need to know what is the angle of the rod. How could we figure that out? Well, we know the length of the rod. We know the angle of theta C, but theta R is not going to be the same because it's not the same size. But what it does share, the rod and the crank both share this X component. That distance is the same because the piston is right above the center of rotation for the crank. So we know that this X distance right here has to be the same. All right, so that distance there is LC times cosine of theta C. So LC cos theta C has to equal LR cosine theta R. You see, because that's the same distance, except that this one is negative because the crank is angled forward, the rod is angled back. So then we can solve out here for theta R. Theta R equals cosine inverse of negative LC over LR cosine theta C. So if we put numbers into that, that equals 2.0 radians equals theta R. So we finished step one. Now step two, to get the angular velocity, we can differentiate the position. So we take this equation, LC cos theta C equals negative LR cos theta R. We differentiate that. So if we take the derivative of each side, we'll get negative LC omega C sine of theta C equals LR omega R sine of theta R. Okay, because derivative of cosine is minus sine, and then omega equals theta dot. Remember out here, omega equals theta dot. So because of chain rule, those theta dots pop out. So we can solve this around and get omega R. Negative LC sine theta C over LR sine theta R times omega C equals omega R. So this right here, this negative sign tells us that the rod and the crank are rotating in different directions, which kind of makes sense because as the crank rotates to the left, the rod is going to be straightening up, so it'll be going to the right. And then as you go around the other side, then it comes back down, so on like that. So if we put numbers into that, we have negative 0.1 sine of 13.1 over 0.2 sine of 2 times 52.36, which equals negative 14.6 radians per second equals omega R. So this is first answer. And we see this negative sign. So really, that's the same as 14.6 radians per second clockwise, because we know that omega R is going that direction. Then the next step is to get position vectors. So for 3, So we need to know our B with respect to A and our P with respect to B. Because we need to know the position of this joint and then the position of the piston. Because we're going to put those position vectors into the cross products to get velocity. So position of B with respect to A is pretty easy. We've got our coordinate frame right here. We know that A is at the origin. So our B with respect to A is just going to be LC cosine theta C in the I plus LC sine theta C in the J. So this comes out to be 0.086 in the I plus 0.051 in the J meters. Then our P with respect to B, that's just going to be the position of the rod right here. So that's going to be LR cos theta R in the I plus LR sine theta R in the J. And remember, we're not calculating this one all the way from the origin because this is the relative, P with respect to B. So we start at B, we go to P. So that comes out to be negative 0.086 in the I, which based on our reality check, we know that if you go forward to get from A to B, then you go backwards to get from B to P by that same distance. So the negative 0.086 and the positive 0.086 have the same magnitude, opposite directions. Good. And then plus 0.181 J hat meters. So now we've got the relative positions of both the points. Next, we need to get velocity of the piston, which we know is going to be in the vertical direction. The piston can only slide straight up and down. It is rectilinear translation. So that'll give us a hint for our reality checks. When we get velocity, it should come out to be something that's just straight up and down. So step 4, velocity Vp. Now we know Vp equals Vp of magnitude, and it's in the J hat direction, just straight up and down. And that has to equal Vb plus V of P with respect to B. Because if we start at A, then we go to B, and then we go up to P. So this equals omega C cross RB with respect to A to get velocity at B. And then we add plus omega R cross with RP with respect to B to get velocity of P with respect to B. Do that cross product down here, we get Vp J hat equals cross product for Vb is going to be, we'll have I, J, K, 0, 0, and omega C, which was that 52.36. And then the components of RB with respect to A, so 0.086, 0.051, and 0. So that cross product plus this cross product, I, J, K, 0, 0, 2, because omega r is 2, and then the components of rp with respect to b, negative 0.086, 0.181, 0. So then this cross product, we do that, it comes out to be, for this one, we'll get negative 2.6 I plus 4.5 J, and then plus over here, we get 2.6 I plus 1.26 J. So this negative 2.6 I and positive 2.6 I cancel, which is good because there's no I component over here, it's just the VP in the J hat. So then we add these together and we get 5.76 J hat meters per second equals VP. So that is in the positive direction, so we know VP is going up. If we look at the picture, we know that as if the crank is in this position, it's rotating towards the left, then B is raising and P is raising. So velocity of P should be in the positive Y direction. That's what we got in this equation. So then to get acceleration, it's a little more complicated. So step 5 is to get angular acceleration. So we need to get alpha r by differentiation. So we take that original of the omega equation. So we take this omega equation, we'll take the derivative to get alpha. So the derivative of that, and we differentiate both sides. Here we'll have to use product rule. So, because we'll have, the length doesn't change, but then omega and theta, omega c doesn't change either, but theta c changes. Now on the right side, omega r might change. And actually, omega r dot is the alpha that we're trying to find. So we take the derivative of this equation, we get negative LC omega c squared cos theta c minus LC omega c dot sine theta c equals LR omega r squared cos theta r plus LR omega r dot sine theta r. Now omega c dot is 0 because omega c is constant. So this we get rid of. Now omega r dot is actually that alpha r. So this is what we're trying to solve for. So then if we rearrange to get alpha r by itself, alpha r equals that omega r dot, which equals negative LC omega c squared cos theta c minus LR omega r squared cos theta r all over LR sine theta r. So we put numbers into here, then we get negative 0.1 times 52.36 squared cosine of 13.1 plus 0.2 times negative 14.6 squared cosine of 2 all over 0.2 sine of 2, which equals negative 1200 radians per second squared, which equals alpha. So because it's negative, we know that alpha is going clockwise. Then finally, last step, we differentiate VP to get acceleration of the piston. And we know the formula for that. We also know that AP has to be in the J hat direction because the piston doesn't move to the right or the left. So AP in the J hat is going to equal acceleration of B plus acceleration of P with respect to B, which from our general planar motion formulas is going to be omega C dot cross with R B plus omega C cross with omega C cross RB plus omega R dot cross with RP with respect to B plus omega R cross with omega R cross RP with respect to B. Okay, so this seems kind of like a big mess, but there's some stuff we can simplify. So omega C dot, we remembered, is 0 because omega C doesn't change, it's constant. And then this part here, this is VB. And then this part right here is VP with respect to B. So keep going down, then AP, J hat, equals, we're going to start putting things into these cross products. So we'll have I, J, K, 0, 0, omega C is the 52.36. And then this other cross product we've already done, that's the VB, which we got here. That's VB, so we just put that in, negative 2.6, 4.5, 0. Plus we have this cross product, omega R dot cross with RP with respect to B, but this is alpha R. So we have I, J, K, 0, 0, negative 1200, and then negative 0.086, 0.181, and 0. So we got RP with respect to B up earlier. And then finally, we have this last cross product, I, J, K, 0, 0, omega R, which is at negative 14.6, what we calculated at the very beginning. And then the VP with respect to B, which is this, 2.6, 1.26, 0. So if we do out these cross products, AP equals negative 235.6 I minus 136.1 J for that one, and then plus 217.2 I plus 103.2 J plus 18.4i minus 38j, which all comes out to be 0i, they cancel, so our reality check is correct, minus 70.9j. Okay, so this means AP equals negative 70.9 meters per second squared. So it's decelerating. Now we will look at a simulation of this. So you can see here, I have defined the length of the crank, the rod, speed of the crank, and then this is just some other stuff about for the simulation parameters. Then Q represents data, so it's crank angle, rod angle, and then I have speed of the rod, speed of the piston, so it'll calculate everything from that. So you can see as the crank goes around, the angular velocity of the rod is in the opposite direction of the crank, and the piston has that rectilinear motion straight up and down. Now we have these graphs to look at. So this first graph shows linkage positions. So the blue is the rod angle, and the red is the piston distance. So the rod angle is in degrees, and the piston distance is in millimeters. You can see that it both follows a sinusoidal pattern, which makes sense. As the piston is moving up and down, that's a sinusoidal, and then the rod moves forward to backward. It doesn't make a complete circle, so that's also sinusoidal. Then looking at the second plot, figure 2 has the velocities. So the rod's speed in radians per second, which is angular velocity. The piston has a linear velocity, and both of those also look kind of sinusoidal, which is fine because velocity is the derivative of position, so derivative of cosine is sine, and so on. So to recap what we did for this problem, we were given the constant angular speed of the crank and the lengths of the crank and the rod, and we need to find velocity and acceleration of the rod and the piston. So we started off finding angles by geometry and integration. And then once we had that, we took derivatives to get angular velocity, and then the derivative of that again to get angular acceleration. For the linear velocity of the piston, then we use the general planar motion formulas for that and also for its linear acceleration.